Today, we are cracking open a true medical mystery. It's a story about an incredibly tough cancer, a promising new drug, and a result so puzzling it forced scientists to dig deeper than ever before. We're talking about the code of cancer immunotherapy.
Let's start with this number, 18 months. It's stark, and it represents a huge challenge in modern medicine.
That's the average time a patient has after being diagnosed with malignant mesothelioma. It's a devastating cancer, often linked to asbestos, and it has such a grim prognosis. For years, doctors have been desperate for better ways to fight it.
So could immunotherapy be the key? The approach that uses the body's own immune system to go after cancer cells? It's a revolutionary idea. The big question was, could it work for a cancer as aggressive as mesothelioma? A major clinical trial was set up to find out.
And that's where the CONFIRM trial comes in. This was a really rigorous gold standard study. We're talking double-blind, placebo-controlled, the whole shebang. They took 332 patients, all of whom had their cancer come back, and gave them either a placebo or the immunotherapy drug nivolumab. Nivolumab basically works by taking the brakes off the immune system, uncloaking the cancer cells so your body can see them and attack. The hope was simple. Give these patients more time.
So the trial finished, the data was all unblinded, and the initial results started rolling in. At first, it looked like good news, but it came with a massive puzzle attached.
Okay, so the trial did hit one of its main goals. On average, patients taking nivolumab went longer without their cancer getting worse. We call that progression-free survival. It was almost 3 months for the drug group versus just over a month and a half for the placebo group.
So you can see it right here. That's a clear, statistically significant win. The drug was absolutely doing something positive. It was slowing the cancer down.
But here's where the story takes a sharp turn. Even though the cancer progression slowed down, it didn't really translate into a big improvement in how long patients lived overall. And when the researchers looked closer at whose tumors were actually shrinking, a very small number just jumped off the page.
Just over 10%. That's it. For all the incredible promise of this powerful new drug, in this really tough cancer, only about 1 in 10 patients saw their tumors shrink.
And this, right here, became the central question of everything. What was so special about this 10%? I mean, if doctors could just figure that out, they could give the drug to the people it would help and spare everyone else an ineffective treatment. The hunt was officially on.
So, the research team basically put on their detective hats and went back to the lab. They took tissue samples from the patients, both the responders and the non-responders, to hunt for some kind of biological clue, a biomarker that could tell them apart.
They started with all the usual suspects. In a lot of other cancers, things like the number of genetic mutations in a tumor can predict if immunotherapy will work. But here, nothing. The tumors from the responders and the non-responders, they looked practically identical on a basic genetic level. It was a dead end.
And don't just take my word for it. The researchers said it right in their final paper. The fundamental genetic blueprints just weren't different. This only made the mystery deeper. They had to be looking in the wrong place.
The real breakthrough came when they stopped looking at the tumor's static DNA and started looking at what the tumor was actively doing, its behavior, its biology, and the whole neighborhood it creates around itself, what we call the tumor microenvironment.
Okay, so the first key idea here is something called EMT. Now, the easiest way to think about this is that it's like the tumor puts on an invisibility cloak. Cells that are going through EMT become more aggressive, they're better at moving around, and they're experts at hiding from the immune system. It's a classic defense mechanism for cancer.
And then you have the complete opposite force, tertiary lymphoid structures, or TLS. These things are incredible. Imagine your immune system setting up pop-up training camps right inside enemy territory, inside the tumor itself. They are packed with the killer T cells and B cells needed to launch a powerful, focused attack.
So you have these two opposing forces, right? The tumor's invisibility cloak versus the immune system's on-site army bases. When the researchers started looking for signs of this tug-of-war, the whole puzzle started to make sense.
And boom, a crystal clear pattern just jumped out at them. The responders, the 10%, their tumors were hot, they were inflamed, they were full of immune cells, they had those TLS training camps, and critically, their invisibility cloak signal, the EMT, was low. And the non-responders? The exact opposite. Their tumors were cold, quiet and evasive, no immune hubs, and a very strong invisibility cloak. So here's the absolute key. It wasn't just about one thing or the other. The real secret, the real predictive power, was in the balance between these two forces. Specifically, a ratio between a key inflammation signal and that tumor evasion signal.
And get this simple ratio of inflammation to evasion, it could predict who would respond to the drug with almost 90% accuracy. This was it. This was the biomarker they had been hunting for all along. It wasn't in the genes, it was in the dynamic biological battle happening inside the tumor.
Now, why does this matter so much? Because this is more than just a fascinating piece of science. This is basically a roadmap for the future of treatment, for precision immunotherapy, where we stop giving the same drug to everybody and start matching it to the specific biology of their cancer.
I mean, just imagine this for a second. A patient gets that terrible diagnosis, but before any treatment starts, a biopsy's taken. It's tested for this specific biomarker. If the ratio shows the tumor is hot and ready to be attacked, doctors can go ahead with immunotherapy knowing it has a great chance of working. But if it's cold and evasive, they can skip it and try something else entirely, saving that patient from side effects and, most importantly, saving precious time.
And that leaves us with a really hopeful idea to think about. By cracking the code of this one trial, researchers might have unlocked a fundamental principle for many other cancers, that the secret to making these amazing drugs work isn't just about the drug itself, but about understanding that delicate balance between the body's power to fight and the tumor's power to hide. A simple test could be the key to making sure the right patient gets the right treatment at exactly the right time.